Thank you very much, Dr. Sundarajan, Dr. Mani Subramanian. I'm very happy to be here at this series of meetings which I'm told are organized every year, and something which is a colloquium on computational aero heat transference structures, the heart of engineering mechanics, if you want to put it that way. And as Dr. Subramanian said, if you know the physics, you can go from one branch of engineering to another. It may take a little while to get used to the new lingo, but the concepts are broadly the same. Now, what I want to do today is talk about aircraft, regional aircraft. Many of you will have heard, and I see quite a few of you here are aerospace people. It's nice to see familiar faces, including from NASA Langley, that I did not expect. There was a lot of discussion, has been a lot of discussion during the last few years about making a regional civil transport aircraft. Well, transport aircraft, civil, military, maybe different versions for India. And during a year and a half, very detailed studies were made. And there was a lot of discussion about whether that should be a turbojet, turbofan, or a turboprop. Now, I have been a fan of, so to speak, pardon the pun, a fan of turboprops for quite some time. Certainly, over the last 5-7 years, for reasons that I'm going to describe to you shortly. But that, of course, if you say you like turboprops, usually become a very old-fashioned man. Turboprops have the public perception of turboprops is their old technology, uncomfortable to fly, slow, bumpy rides, noisy inside, maybe even unsafe. Really the legacy of an older age. But I'm one of those who believe that that may change. And the reason for thinking that it may change, very simply put, is that inherently a propeller is more efficient than a jet. Inherently, that is physics. It's physics, actually. It's not so much technology, it's just basic physics that it's actually going to be more efficient. And during the time when oil was cheap in this world, speed became the driving criterion for civil aircraft design. Even in advance of 0.01 or 0.02 in the Mach number was advertised by the manufacturers as making the fastest civil aircraft of that time. But oil prices have now gone up. There are climate change concerns, and the world is now different. Therefore, you now want to look at those which consume less fuel. Fuel consumption becomes a major driver in aircraft design. And if you take India, our civil air traffic has been growing very rapidly. Our route lengths are different from what they are if you are doing international travel. And Indian passengers, India is a very price-sensitive market. If the prices go up a little bit, the traffic will come down. If the prices fall, the traffic will increase. So it is actually dicey. So in India, it is necessary for us to ask ourselves, what is the kind of aircraft that we need for this country? So my suggestion is that we badly need a modern turboprop, with the emphasis on modern. What will make it modern, and why should we do it? Now, when some of us said this a few years ago, and in fact in the discussions that took place in that committee, it was of course realized that it was inherently more efficient. But by and large, the committee plumped for a turbofan on two grounds. First, there are no new engines on turboprops. Second, there is no new aerodynamics on turboprops. Well, as a matter of fact, I've been for the last 5 years working on precisely that problem, how to make a new aerodynamics for turboprops. But at the time that the committee was meeting, I still didn't have final results on what we had done. But that has changed. The situation has changed. So I'll now make an even stronger case for a modern turboprop than I did a few years ago. Well, but during that time, the perception of the world has changed. Here is what appeared in that well-known magazine, Aviation Week and Space Technology. Many of you will probably read it. And this is called Revisiting Turboprops. And you see what he says there. Rising fuel prices and better technology are shoving RJs aside in a decade or so. 10 years. 10 years is all that this man gives for regional jets. And he says those regional jets will be overtaken by turboprops. Well, I think that's likely. I mean, this is in fact what some of us have been feeling. And incidentally, another person who feels the same way is Kota Harinarayana. So we've been feeling that the turboprop needs another very close look. It is true in some sense that turboprops are relatively old technology because the ones that are flying now were sometimes designed 20 years ago, 15 years ago. So some of the advances that have been made in all these disciplines listed here have not actually been fully exploited in turboprop design. So I want to tell you what we should do and what I'm going to talk about today. In the first place, the world is turning towards greener aviation. Climate change is a serious concern, and greenhouse gases, although the contribution of aviation is very small, a few percent, 2% or 3%, everybody has to be greener. I already said that the turboprop is inherently more efficient. If you look at the structure of civil air traffic in India, and I'll come to that in a moment, it is dominated by routes shorter than 1,000 kilometers. Especially if you look at tier 2 cities, towns, the distances are actually much smaller. It has, the turboprop has this perception problem, but I think it's today it's possible to design a truly modern turboprop. It's not only modern inside, but it will look modern outside as well. And some of these aerodynamics that I'm going to describe widens the range of choice that we have in the aircraft design. We can use this kind of aerodynamics either to increase your speeds, if you think the turboprops are too slow, or improve fuel consumption if you want to fly at the lowest cost possible. Because our market is so large and it's growing, given the right policies in civil aviation, I think India has an unusual opportunity here to do a project which can be internationally interesting. Let's see, page down, is it? Okay. Okay, I see, all right. So let me say just a few words about green aviation before going on. That's the way that the CO2 in the atmosphere has been increasing. You see that last thing out there to the right, that's how it has increased in the last 150 years since the Industrial Revolution. And a lot of analysis made by huge international groups shows that the chances that this will change our climate are getting more and more strong as time goes on. If you look at commercial aviation, it contributes only 2% to greenhouse gas emissions. Nevertheless, everybody will now have to chip in, and therefore, greener aviation is a major project. So the temperature of the world is likely to go up by middle of this century, this 21st century. It will be 2 degrees, 3 degrees warmer, and may eventually be as much as 4 degrees by the time it is 2100. And that can make huge differences to the climate of this world. And oil prices, as I said, have been fluctuating, are now quite high, and all of that changes the economics. NASA has a sugar project, subsonic ultra-green aircraft research, all kinds of sugar, as you can see. Free sugar, refined sugar, super refined sugar, and so on. And they're also looking at how you can cut down, you can make aircraft greener. You can run it on biofuel. That's one possibility. Here's an aircraft, a Falcon, which has run entirely on biofuel on a project in Canada. Here are some stranger aircraft. Look at that solar aircraft at the top. Lots of propellers, by the way. Whole series of them. You have to count them. And there are other methods of improving the aerodynamics. Riblets, for example, surface riblets are known to cut drag. Laminar flow surfaces. These are all known to be possible. However, cost, maintenance problems have actually hindered the introduction of these new technologies. So braced wings may come back, structurally more efficient. Similarly, blended wing bodies with the noise from the jets shielded by the two tailplanes. So there are a whole wide variety of concepts being now considered. Now, what can we do in India? We can wait for those green products to arrive from abroad. We can develop our own green technologies, join green efforts everywhere. But in aeronautics, we have an opportunity now to make green coincide with being economical, which the Indian public love, and being profitable. Otherwise, it wouldn't be done. So I think there is a unique opportunity here. Fuel accounts for a considerable fraction of the direct operating cost in India on aircraft. It is heavily taxed by international standards. And partly because of the policies and partly because of the taxes, the funny thing is that the presence of Indian Airlines in foreign skies now is less than what it was when I first came to the United States. It's astonishing. It's a smaller fraction now than it was in the 1950s. In recent decades, it's steadily gone down. I think our deregulation has, of course, lowered fares, which is a good thing. It also has lowered profits, and many airlines have actually lost huge sums of money. But I think part of the reason for these problems are also technological and business-related. And I want to look at the last factor a little bit more. I want to say a few words about what a next-generation turboprop might be like. On the left there is a turboprop, which is the kind of wing that we are proposing. By we, I mean a team of us who worked on this project. That team includes my colleague, Professor Deshpande, S.M. Deshpande, at JNC, Dr. Praveen, who is actually at TIFR, in the Center for Applicable Mathematics, also in Bangalore, and Rakshit. Rakshit joined me as a student, worked on this project, and is now with Airbus right here in Bangalore. So a wing like that, the one that I have shown on the left, is something that actually provides us with more opportunities for reducing drag or increasing speed, as I said. And I'll show you why in a few minutes. So let me go through this. Nobody can make a successful aircraft in the world now unless it sells in Asia, because it's 1/3 of the market. And the people who have seen this right away are the Chinese, who have a huge civil aircraft industry now, growing very fast. India has been very slow to see this. We still don't have a significant civil aircraft project at all. But if 1/3 of the aircraft are being sold in this part of the world, sooner or later, we will have to start making our own. If you particularly look at the structure of Indian traffic, what is plotted here on the y-axis is the number of seats per week in thousands, okay, that Indian Airlines carry today. And on the x-axis is the route length in kilometers. Now the peak occurs at 500 kilometers. Okay? Now 500 kilometers is good turboprop territory. Really, a jet is not very economical at all at 500 kilometers. But what are we doing? We are actually flying these 500-kilometer routes using narrow bodies. Even regional jets are a very small fraction. In fact, they're so small that they just hug the x-axis here. Turboprops are the green ones. That's the second curve from the top. You can see that the number of turboprops is pretty small. We are using the wrong aircraft for the route structure we have in our country. As you go towards 1,000, regional jets, of course, regional jets and narrow bodies do become appropriate. But just because we have these, and just because the law requires that you fly a certain kind of route, we use the same aircraft for all routes. Doesn't make economic sense. On a 400-kilometer route, which is quite common in India, a regional jet burns 70% more fuel, 70% more fuel than a turboprop. At first, people look at that figure and say, can't be right. It is actually right. Because the jet burns a lot more fuel than a prop does. Well, the increase of oil prices has increased the sales of turboprops, so now the trend is up. It's time, therefore, to look at what we can do with turboprops. What are the advantages and disadvantages of turbojets and turbofans and turboprops? Well, turbofans are faster. In terms of perception, they're seen as much more modern. Cabin noises are lower. They can do more kilometers per day. On the other hand, the turboprop burns less fuel for the same journey. Greenhouse gas emissions are therefore much less. Runway needs are simpler. There are not too many market competitors just now. And if the market is going to increase for turboprops, now is the time to get in. New engines are actually now coming up in the turboprops as well. Actually, airport noise levels from turboprops are lower. The noise footprint of a turboprop at the airport is actually smaller than that of a turbofan. It is timely, and it is what we need. If you look at turboprops in India now, there are two of these. They sort of represent two different ways of looking at what a turboprop may do. This is a kind of economical turboprop, the ATR 72. You see a lot of them in India. This one is a Bombardier Q400. You're beginning to see them in India now. SpiceJet has bought several of them. The Bombardier is more expensive, carries some 10 passengers more or so, is 1/3 faster. It is, because it's faster, it can do more trips per day, so it's slightly more productive than the ATR 72. It is 1/3 more expensive. But if you look at the ATR, it is cheaper to fly, slightly smaller, and in terms of economics, there's nothing to beat the ATR. The ATR largely operates over Asia and Africa and so on, whereas the Q400 operates over the richer countries of the world. It's, as I said, begun in India. This was one of the things that we talked about a great deal, like the RTA 70, without, however, the new wings. Okay. I've already talked about this, so I will not spend a great deal more time. Let me just tell you the kind of certain kind of facts about turboprops. In spite of the fact that turboprops are more popular in Asia and in Europe, I think it has to do with the structure of how far the cities are, the average intercity pair distance. You can see that, once again, it splits roughly 1/3 each between North America, Europe, and Asia. Now, current jets are only 10 years old. Current turboprops are 20 years old. So we actually, there's a good market for turboprops if one is made today. Now, what we need to do in order to make a good turboprop is a judicious mix of economy, comfort, novelty, green appeal. Okay. So can we put together all of this into a new design? That's the question that we have to answer. Well, let me skip this. I'll come back to this if necessary. The problem with turboprops is very succinctly stated here. US customers may accept newer generation turboprops if they can be convinced to try them. That's what this man is writing. But for that to happen, the models have to be available. This means airlines must order them, which they are reluctant to do because customers, etc., etc. Okay? We're caught in a vicious cycle here, and we have to break that vicious cycle. Now, this new aerodynamics is what I'm going to describe to you. Now, there was a mention of computation. Well, it started by mentioning computational applications in engineering. This is one such. This is one computational application in engineering. Looking at how you optimize a wing for a turboprop. Now, that's the kind of software we developed. I mean, everything is done in-house here, written in my group at JNC. I won't go through the structure of that thing, but I'll show you the kind of results we get. What it does is this. Let me tell you what the principle is. If you have propellers, so will you please tell me when I have 5 minutes more to go? Yeah. If you have propellers in the tractor configuration mounted ahead of the leading edge, there's a slipstream going past the wing. From one point of view, the slipstream, because it's moving faster than the relatively faster, is energy wasted. It's gone. But it's not as fast as in a jet. So although energy is gone in the slipstream, you don't lose as much energy lost in the slipstream as you do in a jet. However, there is that energy, and most wing designs don't make use of that energy. And the idea is whether you can make use of that energy and try and find out what kind of wings would make the best use of that energy. Now, when I first started this, I thought this must have been done long ago. So I looked at it right from the beginning, from countless days. Now, occasionally, people have looked at what happens if you put a propeller. But at that time, you couldn't compute. And you had to do linear theory, small perturbations, and so on. Furthermore, optimization was not the kind of discipline that it's developed to be today. So the first thing you find out is that if you have propellers, that old theorem about how the elliptic load distribution is the most efficient is not correct. The load distribution doesn't have to be elliptic. In fact, shouldn't be elliptic. So after this struck me, I cooked up a theory for what you should do if you have that slipstream. I won't take you through all of that. And then we said, well, let's put that on the computer and see what you get using that optimization routine. We have to have properties of the slipstream behind the propeller, which is again computed in the same program. Lo and behold, the first design which came up, almost the first design which came up, looked like this. It said that you'll get lower drag if you have shorter cards behind the propellers with longer cards on either side. Now, once you think about it, it makes physical sense. But for some reason, it doesn't seem to have, nobody seems to have gone through that kind of reasoning. It makes physical sense because the slipstream velocity gives you higher dynamic pressure behind it on the wing. And therefore, if you're looking at lift distributions, if you have the same angle of attack, there will be more lift behind the slipstream because the dynamic pressure is higher. Now you say, well, I want it such that the total induced drag, let's say the induced drag should be minimized. Then it says the right thing to do is to cut down the load that you would otherwise have had behind the propeller when you take the slipstream into account. Well, when you go through all of that and optimize it, you get this kind of wing. Now, I must say that the way that the wing shape has been parameterized in this optimization routine is to make relatively graceful curves on the trailing edge. You don't have to do it. You can do it with linear segments if you prefer. If you wanted flaps and other kinds of control surfaces on the wing, you can make it with flat stretches of the wing, of the trailing edge. But still, the card will be lower behind the propeller than on either side. Now, this one gives us a reduction. This reduces the induced drag by 20%, 19.27%, and reduces the total drag by 8.7%. Well, that's not small. You know, if you're talking about driblets, you're talking 1-2% drag reduction. So it's possible, actually, therefore, to get substantial reductions in drag. Now, how you use that reduction in drag is up to you, up to us, up to the designer. I can trade it for speed and say make the turboprop travel faster. Or I can trade it for fuel consumption, and at the lower speed, make everything cheaper. Either thing is possible. So we went ahead and designed a whole series of wings of this kind with various constraints. Once again. Yeah, OK. Various constraints, actually. Now, we combine twist and card distribution. And the twist distribution is shown here, highly exaggerated. You're looking at it from behind the wing, behind the trailing edge. So if it's black, it means the wing is twisted up. I mean, the card, it's twisted up like that. Highly exaggerated. So with a combination of twist and card, you can actually make substantial reductions in drag. This is a more exaggerated thing here. You can see that in this particular case, the induced drag reduces by 32%, and the total drag by 14%. However, structural engineers will say, well, that looks impossible. I mean, that card behind the propeller is very narrow. And so we have looked at some structural criteria as well. So I can go through a series of wings. You can see how the twist is made here. It is down behind the propeller and up at the tips. OK. So if you wanted to make the next generation turboprop, this is what I think it should be. Cheaper, greener, quieter, at least 20% less fuel consumption, low fares for mass markets, new propeller wing, integrated aerodynamics. You see here, the propeller and the wing should be designed as one system. They're not two different systems because the propeller influences the wing design and the wing design influences the propeller. Quieter cabin, bigger luggage bins, economy comforts, all kinds of new developments, incidentally, in chairs, in seats, which are now sculpted to suit the human body. That's to say, the passenger sitting behind so that you get a little more leg room. Entertainment. I think there are a whole variety of areas where you can actually introduce many novelties, many innovations in turboprop design. So you can ask yourself, what is the maximum reduction that you can make with this kind of approach? It turns out the maximum reduction you can make in the induced drag is close to 13%. But the design which gives you 13% is a crazy design. It will be, from other points of view, totally inefficient. If you look at the ones at the top, they have such crazy trailing edges that they will be structurally impossible. So the structurally possible ones are all around here, the smooth trailing edges. And so if you get 10%, 12%, seems possible with structurally viable designs. So we designed a variety of wings. You can see what is called C there up at the top. It has linear segments for the trailing edge. So if you wanted to put in a flap or something, that kind of design is OK. Then the structures people say, well, it would be nice to have a linearly span-wise decreasing thickness linearly along the span, because then we can put a spar there. This wing will not have a linearly decreasing thickness. So you can change your optimization criteria, and you can do that, and you can see B there. Whereas what is at the bottom shows how it may be if you don't do that. So you can do a variety of things. And we made designs for with the root bending moment as a criterion. All of them, here it is. You see the one on the right here is one where the thickness, not the thickness to card ratio, the thickness decreases linearly along the span. Possible. More or less the same shape. Slight modifications, but it's entirely possible. So then, you see, all of this was sort of lifting line theory put into optimization. But then, if the aspect ratio is not so large, And in any case, these days, you won't necessarily do it by lifting line because you want to optimize the card as well. Suppose you want to optimize the whole surface of the wing, not just the plan form, as we're doing till today. So we've done that with an Euler code. So that's the hi-fi CFD here. And first we compare the results we get from the Euler code with what we get from the lifting line theory thing. So you can see that the lifting line, the kind of theory that I showed, where it predicts 9.3% induced drag reduction. Yeah, high fidelity, high mesh point Euler code says it's about 8%. So there is a certain reduction depending on the aspect ratio, but it's still very substantial, and the two things are close. We actually did the same thing with RANS codes. You do that with the RANS code, and you can see that you get about the same kind of reduction, the same ballpark. Then we did, so another student, Milind Dhake, actually now has written a code which will optimize the whole surface of the wing, okay, both card-wise and span-wise. Well, that has given results broadly consistent with what we are saying here. And so if you wanted to design the aerofoil as well as the plan form all together at one stroke, that also can now be done. And all of them basically confirm the physics behind this. The numbers are very similar, and as the aspect ratio is much smaller, when the lifting line theory would not be so good. 8–9% is something possible for feasible wing design. So we actually made some internal tests as well. And I must thank my colleagues at NAL for getting, my NAL friends got this done at the Institute of Science Tunnel. so I'm very thankful to them. And incidentally, all of this was done as a project from NAL. I must also say that. So I must acknowledge my gratitude to NAL for saying, okay, go ahead, and let's see what we can get in terms of new wings. Now, the greatest surprise here, okay, we took one of the earlier designs, Saras, that was there at NAL, changed its wings, and then we had the old wing and the new wing, put it in the wind tunnel, and find out how much we would save. Now, the greatest surprise here was that the reduction in drag we achieved in the wind tunnel was higher than predicted. Okay, normally you expect, that's theory, you get some reduction. But it turned out that the wind tunnels actually give you a higher drag reduction. So now we have the other difficulty of trying to understand why it is higher in the wind tunnel than it is according to these theories. Well, I think it might have something to do with transition, something to do with constructive interference with the fuselage. We're not testing a wing alone here. See, in the wind tunnel test, it's a full aircraft model. But what it suggests is that actually, if you're doing a full aircraft model, of course, this is only one test. We have to do a great deal more tests than what we have done now. But what the single tunnel test is, that for whatever reason, there are good chances that you can actually make at least that much reduction on a full aircraft. And maybe you can even do it higher once we understand the mechanisms by which that drag reduction has been obtained. You can see here, it's almost 20% lower drag on the left, on the curve on the left. Of course, it increases. Beyond the CL of about 0.7, 0.8, the drag of the new wing becomes higher. Okay. So you can ask, well, is it going to affect your performance during climb, takeoff? Well, that depends on the lift coefficient you use during climb. 0.7 is the crossover. But once again, the codes that we have are sufficiently flexible for us to play off what we need, what we get at cruise, what we get at takeoff, and what we get at landing, and so on. So all of that can be done by optimizing our cost functions. So this seems new, and some people who we showed it to in India and outside said they'd never seen anything like that, so we filed for patents all over the world. And the first one to grant it is South Korea. And we're right now doing it with US, China, and Japan. Well, the rest of it has to do with policy. I don't think on a colloquium on engineering mechanics, that's not a major thing. So I just think that it's possible to do it. Let me put it that way. I think, but however, we'll need to reorganize to do that. And that is something to talk about somewhere else. But I would like to say why India should take the initiative. There is a very large number of appropriate intercity pairs. Our air traffic is growing. Market is price sensitive. Incidentally, by the way, while we were doing this word frugal innovation became very fashionable in India. We discovered suddenly that we were good at frugal innovation. We've been doing it all along. And it reminds me of the man who said, you know, I didn't know I was speaking prose all my life till you told me what prose is. So people have always been innovating, low-cost innovation, frugal innovation. So this is one such. This is an example where it is something particularly related to, particularly relevant to the market in India. But it's not just the market in India. I think the market over all of Asia, Africa, many other countries do that. Incidentally, it has nothing to do with the market in that sense. As I said, this will enable you to trade off. If you wanted to make a faster turboprop, you can do this. This design will work to make a faster turboprop as well. So it's up to you, up to how the designer wants to balance these demands. The aerodynamics is going to be better. So you can do it for speed, you can do it for economy, you can do it for some optimum judicious combination of the two. Okay, I think I have here how we should do it, but I don't think I will go through that. I think we should really make a great deal more tests, more computations. In fact, now I think we are ready for somebody to make a small aircraft with these wings. I'm trying to persuade my friends in defense. You see, there's a UAV called Rustum, which has turboprops. I hope our friends in defense. So we have told them how to do the wing for the Rustum. I know one of these days they will make those wings, and we will know in flight whether these benefits are realized or not. So I end with the same note. The turboprop is coming back, I think. And don't be surprised if 10 years from now, the turboprop looks as natural as regional jets have seen for the last 10, 20 years. Thank you very much.
Sir, you made an excellent presentation. This, as far as I'm sitting here, this is a topic of great interest and importance to India. So I would like to open the floor for a couple of questions, and let me start first myself. You made a very convincing statement here. I mean, there's no argument here. This is India. For India needs short-haul flights. Turboprop is the clear choice, because we are not flying coast to coast, 5,000 miles and all that. Having said that, 4 weeks or 5 weeks back, there was still a tender from Government of India asking for both turboprop and turbofan. So why that still that indecisiveness?
Okay. Well, okay. No, I know about this. I think that people who are looking at this issue are not, well, I mean, to put it in very simple terms, they're not convinced by the argument that turboprops are the aircraft of the future. Now, I think that if you go ahead with turbofans, these are all personal views, incidentally. You go ahead with turbofans, you're following old fashions now already. And when we started talking about this some 5 years ago, there were people who still abroad, people from abroad, say, well, no big market for turboprops and so on. But I'm very happy to see that over the last 5 years, views are changing elsewhere in the world. That's why that issue of Aviation Week is just a few months old. They said regional jets have only a limited life. So if the option is a regional jet, in the first place, the regional jet market is very crowded. In the second place, well, even if you don't take my word for it, if you look at the assessment that's coming up from some people who have been closely involved with civil aviation. If regional jets are going to disappear in 10 years, or shoved aside in 10 years, it doesn't make any sense for us to make one more. There are a large number of regional jets already. Now, if you say, what are the chances that we can sit down and make a regional jet better than one of the new ones now? Say the Mitsubishi regional jet. I'm not sure that there's a good chance of doing anything better at all. In fact, we'll have to work very hard even to meet it. Now, incidentally, if we were to go ahead and make a turboprop, which is what I personally would advocate, I'm not for a moment suggesting that it should all be done in India. That would actually be a mistake. I think we should actually work with somebody else abroad, both to, and this is not a question of nationalism. This is a question of getting a product in the marketplace as early as possible, and with as large a market penetration as possible. I think it helps to have other people who have had some experience in making aircraft. See, if you want to make a civil aircraft, the whole thing is actually a different game. You know, markets, financing, maintenance, support, and a whole lot. India has no experience with it at all in the international market.
Rotors. Yeah. So are we looking the open rotors with that name, modern turboprop, or it's open? It's just
okay. Now, as a question of physics, that's to say, now I look at it as a scientist, not from the marketplace. You can do designs for open rotors. You could gain from new wing designs on open rotors. It will not be the same theory as what I've used, but it will be the same physics. Because if you mount an open rotor, let's say, a little downstream of the leading edge, as many of the configurations today do, then there's only a part of the card of the aircraft which will have the slipstream. So that will change the formulation. Well, that can be done. I mean, okay, we can write another program which will do that. The physics will survive. Now, the turboprop, in the sense, in the technical sense of using a turbine to drive a propeller, may be replaced by an open rotor. But let me remind you that among those sugar candidates, there's a turboprop as well. One of them is the turboprop with a braced wing. And so it's possible. I think that it will depend on how these technologies go. Open rotors, are very noisy. I don't know how they're going to handle the noise problem. After having said turboprops are noisy, maybe you want to go to something which is noisier. We don't know how that will work out. It's hard to tell.
So does it mean that in this presentation, it is use the tractor configuration?
Tractor, yes.
So, but open rotor, as far as open rotor is concerned, more favorable going to the pusher type rather than the tractor.
Okay. Once again, physics. Now I become an academic. You tell me exactly what your configuration with the open rotor is. I'll tell you how to design a wing for that particular application. Okay? It can be done. So the fundamental issue is really how to exploit the energy in the slipstream to improve your wing performance. The fundamental conclusion is it is possible. And these theories and internal tests show that the improvements you can get are significant. They're not to be laughed at. We're not talking about 1% or 2%. But people are willing now. If they're sure about 1 or 2%, they will do that. So that physics will survive. So you tell me what open rotor configuration is a popular one or an attractive one. We can tell you how to design the wing for that kind of open rotor.
Yeah. My doubt is, can we use the same wing with the same turboprop?
No, not the same wing.
No, same turboprop. Instead of using the tractor version, if you use the pusher version of the same proposed
pusher version mounted where? At the back?
Back, yes.
No.
Okay.
See, you can't. Because, once again, going back to the fundamental physics, this exploits the higher velocity, higher dynamic pressure over the wing, which is in the slipstream of the propeller. Now, if you mounted it at the back, you can't exploit that slipstream. Maybe you can exploit it on the tailplane, but not on the not on the wing.
Thank you, Professor.
Thank you, Professor, for a lovely presentation. My question is related to the shape of the wing, the trailing edge that you described, where the chord is smaller in the slipstream area. So do we have, even if you take that 10% efficiency improvement design, which has the least change in the trailing edge, even then, do we have any structural buy-in in terms of experiments or in theoretical calculations? So is it practically possible to have that? Because I'm saying that not only you have the smallest chord in that area, but you are also loading that area with the engine weight.
Okay. Now, we haven't actually made a detailed structural analysis of it, and that has to be done.
But do you see it as a positive?
I don't see that as a major factor for the following reason. First, there were questions about cost of fabrication. Well, my friends who do composite technology here at NAL, my colleagues of Shyam Chetty and myself in earlier occasions, they tell me, well, if I'm using carbon fiber composites, we see no problem why we can't make that wing, that shape and so on, including a smooth curve if you wanted one, or one with straight segments if that's what you wanted. Now, as far as the structural design things go, what they've told me is that, if you can get, see, you don't even have to design with sparse as we used to earlier. Okay, there are now many other options in structural design. So although this is not based on detailed analysis, the general response of people from structures is, well, if you can get the thickness very linearly, so that I can put a spar, we see no problem. But if you, that anyway can be handled. That's not a problem aerodynamically. And in particular with our new code, which does a full three-dimensional simulation, Euler. The kind of thing that you're talking about doesn't seem to be a serious problem. I mean, we are talking about, 10% change in the local load. But I don't think that's a serious problem. We have done optimizations with wing root bending moment, about how much do you lose in wing root bending moment if you use these designs. It may go up somewhat, but discussions with people who are experts in structures seem to suggest that they're not going to be serious. But all of this is just a qualitative assessment. No quantitative studies have been made.
Thank you.
Yes. Thank you very much. I think in the best interest of time, I already take 20 minutes late.
Yeah. So thank you so much for your very thought-provoking lecture. I think it's about the basics of engineering, which seems to be the most important thing that everyone seems to forget when they leave the college and get into industry. So that's something that is very interesting. And the other one that, being a structural engineer, the constant clashes that we have with Mani's team from the fluid side, we never seem to ever agree on anything. So this is another area that I think within our own community, we need to start working together to be able to make better products. Thank you so much.
Are you born to engineer?